Salutations, Internet. Good time zone. All right. So last week's video went on for way too long. I don't like going above 30 minutes on my video, so hopefully this video will be shorter. I'm going to do my best. However, it looks like this particular topic won't be resolved with this video, so I'm going to see if I can squeeze in one more video before the end of the year. We'll see how well I do. But without further ado, let's pick up where we left off. So we did a lot of stuff last video. We have our equations for Lambert's problem. We have our constraint for Lambert's problem. And let's get all three of them on the screen. I have a radius and a velocity equation in terms of the perifocal reference. So P, Q, and W. W, again, doesn't really do a whole lot in this particular scenario, so we are going to gently ignore it for at least the majority of this video. So we're going to come over here to actually do all of our writing for this video. And I have taken the liberty of just copying down the the radius and velocity equations from the previous video. So they're all right here, nice and neat. You will see that we have two equations that are in terms of P and Q, actually. So I'm realizing that if I don't fix this now, this is going to bother me. So give me just one moment. If I start with a curly brace, I should end with a curly brace. And yes, I know I have two curly braces right next to each other. I'm doing the best I can. All right. Yes, we have things in terms of P and we have things in terms of Q. That, to me, tells me that we can use some matrix math. We can convert this into a matrix equation setup so that we technically have one equation that we are solving for. But matrix math is really handy in that I can solve a bunch of different equations at the same time, all in terms of each other even. That's going to be a whole topic for another series. That's actually going to be the control theory series. I can't think of the word. That's actually going to be the control theory series. I'm not going to do linear algebra necessarily. We'll do some review of linear algebra here, but if you want the control series, the control theory series, I'll be working on that one in the future, and I'm going to try to remember to put in a card here to get that set up. Anyway, now that that's out of the way, to convert this into a matrix equation, you're going to put the r vector and the v vector into a bigger vector, and it does work this way, where we can have even a vector of 3 and a vector of 3 to create a giant vector of 6. That is not actually what we're doing with this one. I'll finish writing the equation because I have a specific spot where I want to put this. So I will then create a matrix C that I will define here in a second. And that is going to be multiplied by P hat and Q hat. And all right. So we have C. C is going to look like everything that we did not include, but the order and spacing does matter. So we have, for the P element of R, we have this term, this R naught times cosine of theta naught. The Q element for our R is going to be then R naught times the sine of theta naught. P element for our V is going to be minus mu by h times the sine of theta naught. And then the Q element of our V is going to be mu by h times the quantity. There we go. Times the quantity of the eccentricity plus the cosine of theta naught. This, I'm gonna write it in blue, is a 2x2 matrix. For those of you who didn't take linear algebra, first of all, I highly recommend that you take linear algebra. Second, this is just a declaration of how big is this matrix that we are working with, right? We can have it for vectors, like this one over here is going to be in space 2x1. It is 2 tall and 1 wide. You can also do it for scalars. That's just going to be the fancy R of 1 times 1. But tangent over, now that we have created a matrix equation, now that we have rewritten our equations in the form of linear algebra friendly matrices and vectors, we want to invert everything so that we can solve for P and Q. Because going over to here, we have our R, our radius, in terms of P and Q. And this radius can change throughout time, but it needs to be in reference to P and Q. I guess the way I want to describe it is the most straightforward way of doing that is to define P and Q. We want to define our P and our Q in terms of the initial R and V vectors. And in fact, these are the initial R and V vectors. I just left the subscripts off. So to do that, we are going to invert our matrix C and multiply it by R naught and V naught, the R naught V naught vector, the position velocity vector. I don't know what I want to call that one. It's just going to be RV vector for now. All right, so we haven't done anything too crazy here. We've inverted a matrix, which, I mean, we do that all the time when we look at something like y equals m times x. We want to solve for x. Okay, that's going to be y over m. Another way of writing that is going to be m inverted times y. It's really just the same thing. What that means here for a matrix, though, is we're going to take up a little bit of space doing this, but I think it's generally well worth it. Let's see. So C inverted is going to be equal to 1 over the determinant of C times, and then these two will swap places with one another. So I'm going to need more space. There we go. That will be mu by h times the quantity of E plus the cosine of theta naught. Now, I have a thing where I like to write my matrices going down, and then I'll jump over to the next line, as opposed to like how I would read across and then down. Small detail, but don't get too confusing. I declare it so that you hopefully can keep up with me. Anyway, so we're swapping these two around. Now we need to negate these two. So that becomes positive mu by h times sine theta naught, new column, minus r naught times sine of theta naught, down one row. This one, that's the one I want. So r naught times the cosine of theta naught. All right. And again, just as a refresher for anyone who hasn't taken linear algebra yet, or if you have taken linear algebra, but it's been a little bit, the determinant of a matrix, which I will be writing it as line matrix line, is well, to give a smaller example about it, if we have our matrix M as A, B, C, D, the determinant of M is not a matrix, but a scalar. It is A times D minus B times C. It gets a little more complicated when you have more dimensions, but this is the long and short of it. So, no, I will definitely want more room. Let's do this. That's the determinant of C is equal to these two multiplied together, where we will have R naught times mu over H times the quantity of the eccentricity plus the cosine of theta naught. And then I have minus, it is minus the next combination, which is these two multiplied together, which is actually minus R naught mu over H. I'm going to go ahead and cancel out the negatives. And then sine times sine is sine squared of theta naught. And I already realized my mistake. So let me fix it really quick. Nope, I lost. Go. My mistake was that I did not multiply the second part. Sorry, one second. I did not multiply this cosine times this set of terms up here. So to rewrite that, we're going to have E times cosine of theta naught plus cosine squared of theta naught. That's actually going to be really important here. Let's scroll down. Now we have the determinant of C being equal to, all right, we have R naught mu by H, R naught mu by H. That's a common term, so we can just take that outside. R naught mu by H times, we have three terms inside of all of this, actually. So we will have E times cosine, cosine squared, and sine squared. Sine squared and cosine squared is 1 plus the eccentricity of cosine of theta naught. So now we have R naught mu by H times 1 plus the eccentricity times the cosine of theta naught. Well, we have an R here, we have a mu and an H, and I think you know where I'm going with this. We go over to the equation sheet. we have the orbit equation, radius, in terms of h and mu. So let's go ahead and I'm going to write it like this, h squared by mu times, I'm going to do that, 1 plus the eccentricity times cosine of theta naught. And it does need to be theta naught because this is r naught. These are the initial conditions. We're looking at the initial condition for radius. It has to be the initial condition for the true anomaly angle. That is inverted times mu over h. Give itself some space. Times 1 plus the eccentricity times the cosine of theta naught. All right, now comes the fun part. We get to cancel out some stuff. So let's start by getting rid of this big thing here. And then the mu's can cancel out. And the h can cancel out with one of the h's in the numerator. So at the end of the day, the determinant of c is just the angular momentum. In the two-dimensional case that we're looking at right now, it is the scalar of the angular momentum. But in the third dimension, the angular momentum is actually kind of defined as, well, maybe not defined. It is the determinant of c in the w hat direction. So there we go. I guess we did use w in our video today, but that's about the last time that we're going to talk about it. So we have the determinant of h. We have, with that, we can make the inverted c, and from that we can find out what p hat and q hat are. And I am going to go ahead and write those in over here. So our p hat is going to be equal to u by h squared, times eccentricity plus the cosine of theta naught times the radius plus the negative r naught over h times the sine of theta naught times the velocity. And I'm not going to do a lot of scrolling up and down. I will, however, do this just so you can see that no, I am actually doing things right. So we will add an h to the denominator on both of these terms and appropriately place in an r and the v. And actually, I will do this. Now, q hat is equal to u over h squared times the sine of theta naught times the radius vector plus what will end up being r naught over h times the cosine of theta, the cosine of theta naught times the velocity vector. All right, so this is actually not the final point of the video. What we are actually going to do is we are going to take our P and our Q, we're going to plug them back into this because we want to find whatever our r and our v is for an arbitrary point in time in the future. What we needed, though, was a good definition of what p and q are. And the best way to do that, at least from what I've been seeing, is to define p and q at a point. The point that's been given is the initial point. So why not? Why not start with the initial point and propagate forward from there? And that's what we're going to try to tackle in the next video. And like I said, I hope I can get that out within a reasonable amount of time. Hopefully I can squeeze that in before the end of the year. Until then, thank you all so much for stopping by.